Hello, welcome to ISC. I'm Igor Sfiligoi, and I'm here to present our experience running a pre-exascale geographically distributed multi-cloud scientific simulation. I did this together with friend Würthwein, Benedikt Riedel, and David Schultz. Now, let's start with the big picture. What we wanted to do is create the greatest possible high-throughput computing pool using GPU instances from all major cloud providers. And we wanted to do this without using any reservations or long-term commitments. We wanted to do it in the shortest amount of time possible. And and the most important thing, we want to do it running a real scientific application. We didn't want to do it just as a computer science exercise. We did it, and we picked about 51,000 GPUs, which turns out to be about 380 32-bit petaflops. How big is that? Well, for comparison, the #1 HPC system currently in existence, Summit, provides about 400 petaflops. So we were not that far away. Let's start with the science. The science we supported was IceCube. IceCube is a detector at the South Pole. They instrumented about 1 kilometer cube of ice with digital optical modules. And while they have a very wide range of science they do, the major emphasis on detecting neutrinos, because there are not many other instruments that can do it. Why neutrinos important? Well, because they are essentially the only ones that can allow us to see about 20% of the universe. That 20% of the universe is pretty much dark to traditional astronomy, so you need a new set of messengers to see it, and neutrinos are one of them, because they can travel through pretty much anything without being stopped. So if neutrinos are really that hard to stop, how do you see them? We use something called Cherenkov light, which is basically a sonic boom with light. Cherenkov light appears when a charged particle travels through matter faster than the light can. It's not faster than the speed of light, but in the vacuum, but nothing can go faster than that. But it's still faster than what light can do in that medium. And here in the bottom, you have a classic example that usually show, which is a nuclear reactor that seems blue, and that's not the light coming from the reactor itself, but it's because the particles that emanate it go faster than the speed of light. For IceCube, we do this with neutrinos, who, when they travel through ice, create light, and we can detect it with the optical modules that you see depicted here. Ice is a great medium. It's solid, yet transparent. And IceCube decided to go to the South Pole because there was a lot of ice already there, so we didn't have to create artificial ice. However, using natural ice has its own disadvantages. Since it was deposited over millennia, its ice properties are not homogeneous. Here you have the plot that shows how the scattering coefficient changes with both depth and wavelength, and you see it's anything but fixed. So the light, when it's created, travels in all kinds of directions before hitting the optical modules. And here is where science and compute meet. IceCube need to do a lot of detector calibration via ray tracing simulation in order to properly characterize the ice. And they need several exaflop months of compute in order to do that. It happens that GPUs are very effective for computing photopropagation, definitely orders of magnitude more effective than CPUs. And IceCube standardized on OpenCL, which makes it easy to use any kind of GPU type. This kind of calibration is also an intrinsically and high throughput computing problem, because each photon is independent. It's basically a statistical problem. So that's about the science. Let's now switch off what we actually did and what the computing setup looks like. Let me start by making clear that IceCube already is doing HPC at scale through the Open Science Grid. And they use HT Condor as its workload management system. They use HT Condor because it's great at this task, because it makes it trivial to join any kind of compute resource into a single HPC pool. There are no special networking requirements needed, so no VPNs or similar, and it assumes shared nothing. So adding cloud resources is really trivial to add to an HD Condor pool. However, what we wanted to go big. We wanted to create the biggest possible pool ever made and do it faster than anyone else had ever done. So we decided to go with a dedicated setup on a dedicated hardware, although the configuration was not that much different compared to what they do on the Open Science Grid. We know that HD Condor's major scalability limit is the rate of resources that can join the central manager, the so-called collector. And this is due basically because of the initial security handshake. We use strong security between all the daemons in the Condor pool. And the initial setup is quite expensive, and then becomes much, much cheaper because all the security is pre-negotiated. Luckily, one can work around it by creating a tree of collectors, and you have an example here. In this setup, the worker nodes or VMs in the cloud talk to one of the leaf collectors, and those leaf collectors spread the load among all of them. And since they are long-lived, the propagation to the central collector is cheap because the channel was already pre-negotiated. So that takes care of the major scalability limit of Condor. We also went with enabling external IP or public IP on all the VMs in the cloud, which happen to be not set up, but that's not a big deal for Condor. Condor can also work with just outgoing connectivity, but then its scalability is limited. Reversing the connection takes some additional machinery in place, which is works well enough at steady state, but with very burst environments, it's not good. So since we could do it and the cloud allow us to do that, we did it. Let me just briefly mention what we did about data. As I said, the goal was to do a very bursty setup, very fast ramp up. And in that case, a lot of data would have been needed in very short amount of time. Normally, IceCube reads their data from their central repository and stores it back in the central repository, but we didn't want to add a data challenge to this exercise. We really wanted to understand how much the cloud can scale, not how much the IceCube storage can handle. So we pre-staged all the input data in the cloud storage, S3 on Amazon, Blob on Azure, Google Cloud Storage in Google. And also all the output of the compute went back in the cloud storage. And also all the software that IceCube needed was pre-installed in the VM images. So during the cloud burst, no data needed to get in and out of the cloud apart from the command and control to the central Condor collector. Now, of course, we had to move data in and out of the clouds eventually, but it was done all asynchronously, and it was not strictly part of the exercise. Now, we didn't want to change how user jobs look like. So we created simple wrappers that abstracted away the fact that data didn't come straight from IceCube and went back to IceCube storage, but went to the appropriate local cloud storage. So jobs were completely oblivious of the changes in the storage. So that's about how our setup looked like. Now we were ready to go and provision the resources. Now, the expected burst rate was higher than anything that anyone had tried before, or at least we're hoping that would be the case. So we couldn't really use any existing multi-cloud provisioning tools that were certified of those rates because nobody had ever tried before. And we definitely didn't want to try and debug third-party software. So we said, let's just go with the native cloud APIs. And one reason was because they were expected to be the most performant, so we could get the highest burst going that way. And measuring how bursty you could actually be was one of the desirable outcomes. It turned out that native cloud APIs were also very easy to use, especially when you want to do a one-off exercise like ours. Just be aware that each cloud region is completely independent. even inside a single cloud provider, and we use 3. And here you see an example for AWS. Here you see the list of region for Azure. And here I have Google. But the exercise turned to be easy because all clouds are essentially the same. Now, they do have slightly different implementations behind the scenes, but the concepts from the user point of view are very similar. We ended using group provisioning mechanisms for all 3 cloud providers. We used fleets in AWS, virtual machine scale sets in Azure, and instance groups in Google. Slightly different implementations, slightly different semantics, but actually very, very similar concepts. For the images, we created a different image for the 3 cloud providers because we wanted to use the cloud native tools, and different cloud providers did need a little different drivers. In theory, we could use the same image and parameterize it, but having only 3 cloud providers, it was much easier to just create 3 different instances. However, inside a single cloud providers, we parameterized for the various regions because there are tens of regions in each of the cloud providers. We used the cloud metadata catalog to discover where we were running, and then parameterize, fetch the right configuration during boot time. The images were completely self-contained, so no external input was needed. So that's about our setup. We, of course, did a lot of testing on small scale to make sure we could actually achieve what we wanted. But at one point we said, okay, we're ready, let's do it. Before going into the result, let me just remind you that the goal of this exercise was to do it without any reservations and no long-term commitments in place. We just wanted to grab whatever was available at that point in time. So we could have done it completely anytime. There was really no advanced planning or agreement with the cloud providers when we would do it. That said, setting up the accounts was not exactly trivial. Apart from the building part, which is a problem on itself, depending which institution you come with, the major problem you get when you create a cloud account is that it comes with very low default quotas. Now, you should understand that quotas do not guarantee that you will get those resources if you try. They just limit you what you can actually try. But they do limit the financial risk of the cloud providers. Because if you can create a pool that burns a few $1,000s a minute, you can very fast get to $1 million bills. And when you get a $1 million bill, if you cannot pay it, it's the cloud provider's problem because they could have sold those resources to somebody else. So it took many rounds of meetings to get those quotas raised. Essentially, we had to convince the cloud providers that we were capable enough of not wasting those resources and were willing to pay whatever we consumed. So it was quite a bit of a social hurdle, but we convinced them. But the good news is you only have to do it once, and then you can run as many times as you want. If you have an institute do it for you, you may not even need to do that. In our case, we didn't have that pre-established, so we had to do it all by ourselves. So having that, we went ahead and did it. We picked a Saturday, November 2019. We said, well, Saturday is likely when there are most resources available. We went from 0 to max in about 2 hours, although there were 2 bursts. You see, the first burst was about half an hour, then you see this flat, and then another 1 hour burst. This was because we actually found a setup that only showed up at large scales during our work, and we fixed it in real time and then did the second growth. So we probably could have done it in like an hour and a half if we knew what we know now. But it was quite a success anyway. We picked at around 51,000 GPUs spread over many, many regions. That was about 380 floating point 32 petaflops, as I mentioned before. If you look, you can see that no single region provided the majority of the resources. So we really had to go wide to get to that peak. Unfortunately, I cannot tell you which cloud providers provided which one. I'm not allowed to, but I can tell you that not single one provided the majority. And we also had to go very wide geographically. As you can see, while the US provided a lot, there was still quite a lot coming from Europe and Asia. And finally, we had to use 8 different GPU types in order to get to the total. Let me switch slides for a little more details. Here I have the actual numbers of what we got at peak. And one thing to notice is that the older GPU types dominated the wall clock time. They dominated the raw number of instances we got at peak. But most of the petaflops actually came from the newer GPUs. And you can see it here. Here you see that the older GPUs have most of the count, but the newer GPUs really provide most of the petaflops. So just counting the number of GPUs doesn't tell much, because the difference in performance between different GPUs, it's quite huge. Here I have a similar slide, but with integrated petaflops. Slightly different numbers, because we didn't get all the GPUs running all the time, but the story is not that much different. Now, when you look at the cost, you see that the amount you pay changes a lot based on which GPU type you pick and from which provider. And even within the same GPU, sometimes you have different setup of the VM that can change the cost of the resource quite a bit. But all of them are built by time, and we try to use spot preemptible instances whenever possible, because they are about 3 times cheaper than the on-demand ones. And here I have the estimated, well, the list price of the various GPU types. And it varies a lot, because different cloud providers have different cost structure. And this was correct in the beginning of this year. It may have changed by now. Cloud providers do change the values. But if you look at the cost effectiveness, you would see that newer, and especially 32-bit optimized instances, tends to be way more cost effective. Take, for example, the T4, which is pretty much the newer member of the GPUs. It's 32-bit. It's not very powerful by itself, and it's 32-bit optimized, but it's very cheap. So it's about 50% more effective than the top of the line V100, and definitely more cost effective than the older GPUs like the K520s. And that it's even more true when you look at actual science output that you get from those GPUs. Here we have the runtime of IceCube photopropagation simulation for the various GPUs. It's not completely the same. It's distributed, because different inputs will give you different outputs, but that's the average. And you see that the newer GPUs are way faster than the ancient ones. And when you compare the runtime compared to the theoretical teraflops that a GPU can provide, you see that newer GPUs run much faster on the same number of teraflops than the old ones. So the amount of science you get out of a GPU compared to the wall clock time, or even the total cost, is heavily skewed toward the newer GPUs. So we got way more science out of the newer GPUs than the older GPUs, and for a much lower price. So picking the right amount, the right kind of GPU, if you can choose, it's very important, both in terms of how long it takes and how much you pay. However, when you want to go for the largest possible pool, you take whatever you get. And getting a quarter of science out of the old GPUs was definitely worth it, even if the cost was a little high. And that's all I have. Just to summarize, I believe the cloud is definitely an option for large-scale computing. We show that there is plenty of capacity in the cloud. At least that was the case in November 2019. And we reached about 380 32-bit petaflops, which is almost the size of the highest HPC system currently deployed, which is Summit. It is relatively easy to provision pre-exascale HPC system, and you don't need any advanced planning or long-term commitments. And we demonstrated you can run real scientific computing on it. Let me stress, this was not just a computer science exercise. We actually got real scientific value out of it. But flexibility is definitely key. No single cloud region provided more than 10% of the total resources, and no single cloud provider delivered anywhere close to the majority of those. Moreover, we had to use many GPU types too, with no single GPU type providing the majority of compute. So be flexible and you can get a lot off to the cloud. And this is really all. I want to thank NSF for their support. And these are the sponsor of ISE. Thank you.